Yes,
Yeah.
we can see the slides. Yeah.
Yes.
Okay. So I want to welcome all my fellow scientists, welcome everyone interested in service life prediction. Thankful to have friends in your country and friends in your research laboratories in India. I know that it's an honor for me to try to help you, and I hope that this presentation is helpful to you. It's fantastic that we could be together. I'm very thankful for the opportunity and glad that technology makes this possible. I know that you have exciting and successful research ahead for you this year. So today we're going to talk about service life prediction. Can you see my arrow?
Yeah. Yeah. Yeah.
Okay. So here's an outline that the topics that we want to cover. First, I call it a list of metrics to consider when you're doing service life prediction, and then an example of service life prediction modeling. And then at the end, if we have time, I call it 4 additional topics for depth of understanding. And these are the techniques that are involved in service life prediction with some more detail. So it's explanation of oxygen consumption measurement technique, how to determine shift factors and generate a master curve, explanation of beta, which is the effect of oxygen partial pressure on oxygen consumption rate, and brief explanation of the diffusion limited oxidation model. Okay. So, you know, the question is, what is the key damage mechanism governing the life of the part? I mean, that's how to get started. And this is kind of my reminder list of you know, how to approach it. You know, you'd like to, ideally to get a new part and a part from service, you know, like 3-year, 4-year, 5-year of a part after service, able to obtain that. They're not easy to obtain. And the way I think about it is shown schematically here. You know, sometimes I start with modulus profiling. If the modulus increases, then I think maybe oxidation, and I think about these tests: oxygen content, cross-link density, soluble polymer, soluble sulfur, tensile properties, density, DMA strain sweep, pulse proton, time domain NMR, cross-link distribution, AO concentration. And if I need to dive deeper, peel strength, tear strength, crack growth rate, and then further on, you know, oxygen consumption rate, developing a time temperature Arrhenius model, and then asking the question whether the rubber is a crystallizing rubber. If the modulus decreases during service, I think possibly thermal reversion. And then I think about these tests: cross-link density, cross-link distribution, soluble polymer, soluble sulfur, DMA strain sweep, pulse proton, time domain NMR, tensile properties. And then I ask the question whether it's a crystallizing rubber. So today we're going to kind of be in this one, and we're going to do tensile properties and what we call ultrasensitive oxygen consumption rate technique. Okay, develop our prediction model, and we're also going to use Arrhenius time temperature superposition. Okay, so first I need to apologize. So our example of service life prediction is for tire durability, life of the wire coat compound at the belt edge of a passenger tire. However, we want to emphasize the techniques are applicable to any most rubber, application uses, parts, molded goods. And then most of this work was funded by National Highway Traffic Safety Administration, NHTSA. And this has all been published on the NHTSA website. However, I have to say that the opinions, findings, recommendations contained herein are those of the authors and do not necessarily represent those of NHTSA. So NHTSA asked the question, is it possible to predict service life of the belt coat compound in a passenger light truck tire? Tire that was selected for the study, BF Goodrich Touring TA P195/65 R15. New tire was provided by NHTSA. The tire was dissected to retrieve the belt coat compound taken from between the belts, excluding the wedge compound. And we're going to jump to the assumption that the major damage mechanism is oxidation. This will be talked about thoroughly next week when we talk about the chemical mechanisms of aging. Okay, so I'm skipping now to the last slide. Okay, and here we compare the predicted elongation to break results to the actual entire service elongation to break. So the pink squares are tires that were retrieved from people and users like you and me in Phoenix, Arizona. So this is a 6-month-old tire that was retrieved from service, a 1-year-old tire, a 2-year-old tire, a 3-year-old tire, 4-year-old tire, 5-year-old tire, 6-year-old tire. So that's, real life data. And the blue diamonds are model predictions. Okay, so this is time in years at 22.6 degrees centigrade, which is the average annual temperature in Phoenix, Arizona, where the field tires were obtained. Okay. So the whole talk is how did we come up with this prediction curve? Okay, so these are the steps that we took. We measured elongation to break as a function of time at a series of temperatures and obtained the aging kinetics. And then we used oxidation kinetics that are ultra-sensitive oxygen consumption technique. And here you'll see what I mean, but the whole purpose is to obtain the shift factors, okay? We know the shift factors, then we can shift our data onto any temperature within the range of our data measurements. And then there's 2 additional topics that come up, We'll get to this point in the project and we'll realize the model's lacking so very, very badly, terrible. And so what's wrong with our model, And we took a we said there are probably 2 things that are missing in our model. One is the fact that we did not include the effect of oxygen partial pressure. That means the inside cavity of the tire is inflated, so it has higher than atmospheric oxygen partial pressure. And The second thing we forgot to incorporate into our model is the duty cycle. In the NHTSA statistics, on the average, tire is in service 4% of its life. 4% of its life, it's a rolling tire, and 96% of its life, it's a static, stationary, parked tire, inflated tire. So we took into account the duty cycle, and the way we incorporate the duty cycle is using the diffuser limited oxidation model. Okay, so that is the outline of how we obtain our service life prediction model. So we're going to talk mostly about aging, getting good aging data, and then using the ultrasensitive oxygen consumption technique to obtain the shift factors down to 22.6 degrees centigrade. Okay, so here we start off. Now here's our elongation to break as a function of time and days. Here's 55, 65, 80, 95. So here's the 95 degree elongation to break as a function of aging time, and here's our 80 degree data as a function of aging time, and then here's our 65 degree data, and then here's our 55 degree data. Okay. So what we're after, these shift factors, these are, so we're shifting horizontally to obtain these shift factors. So we shift all the data onto 80 degrees. So the shift factor is 1. Shift factor is a relative rate, so multiplication factor of 1. So the 80 degree data is not shifted. The 55 degree data is shifted onto 80 degrees. 65 was shifted onto the 80, and then the 95 was shifted onto the 80 degrees. And so these shift factors are relative rates, right? So rates. And so once we know the rates, we're going to do an Arrhenius plot, right? We plot the log of the rate as a function of inverse temperature. And then you can understand the mechanism and shift the data. So here now we feel confident. We know between 55 degrees C and 95 degrees C, but we'd really want to get down to 22.6 degrees C with confidence, So for that, we use the ultrasensitive oxygen consumption technique. So here's oxygen consumption rate as a function of aging time, 20 degrees C, 30 degrees C, 45, 55, 65, and 80. So here's the 20 degrees C. These are measurements of oxygen consumption rate as a function of time. And then the 30 degrees C data, 45 degrees C data, 55 degrees C data, 65 degrees, and 80 degrees. Okay. So now we know the oxygen consumption rate and the amount of time. If we know rate and time, we can calculate the integrated oxygen consumption. So here's the integrated oxygen consumption as a function of aging time. Here's the 20 degrees C data, 30 degrees C, 45 degrees, 55 degrees, 65 degrees, and 80 degrees. Okay. And so you can see we can, horizontally shift and generate a master curve. So using time temperature superposition of the integrated oxygen consumption results, we obtain the shift factor. So we're shifting all the data onto 55 degrees. So now we have the shift factors from 20 degrees C to 80 degrees C using oxygen consumption techniques. Okay, so now we can combine all the shift factors. So here is our shift factors as a function of inverse temperature plotted on Arrhenius plot. And the blue, dark blue diamonds are the results from the oxygen consumption rate. Somewhat hidden, but they're right here. And then here is a CO2 generation rate, pink squares. And then the carbon monoxide generation rate, gold triangles. And then here's the tensile properties we obtained at the beginning of the, and so here's the tensile, so not 95, 80, and 70 degrees. So those are the asterisks, purple asterisks. Okay. So and then in our technique, we also obtain a volatile organic, and the volatile organic is shown there. So the volatile organic presumably is governed by some other mechanism in addition to oxidation, because it falls on a different line. So we're going to use this black line for shifting, our data to 22.6 degrees centigrade, which is going to be about right here. This is our 20 degrees. If you remember, this is our 30 degrees, our 45 degree day. And you can see if we only had the tensile data, we would not have confidence in our extrapolation down here to the temperature where we want to get. And oftentimes we see that there's non-Arrhenius or non-linear data down in this generation. Although with this data that we have, I think the linear fit is the best. Okay, so now we can shift our data to 22.6 degrees C. And now here's our predicted curve, and here's our actual in-service tire results, rubber extracted from tires in service, and measured elongation to break of the belt coat compound. And we say awful, terrible, couldn't be worse. We're totally discouraged and disappointed how badly we did with our model prediction. So we scratching our head, and we came up with two ideas, and one idea is we forgot to incorporate the fact that there's a higher oxygen partial pressure in the cavity of the tire. So that might be true in many other applications that you're involved with, hoses or so on. And secondly, we forgot to incorporate duty cycle. That means 4% of the life of the tire is a running tire, which the temperatures inside the tire, the belt coat region, are considerably higher than room temperature, ambient temperature. Okay, so we started, next thing to do, to try to incorporate those two things into our model. Okay. So our proposals, the missing factors are the belt coat compound in the tire is subject to a higher oxygen partial pressure from inflation pressure than provided by atmospheric oxygen partial pressure. And the in-service tire spends a portion of its time as a running tire. We assume the national NHTSA reported average for running tire to be 4% while in service. 4% of its life, it's a running tire. Okay, So first is to incorporate the effect of oxygen partial pressure on oxygen consumption rate. We measured oxygen consumption rate as a function of oxygen partial pressure at three temperatures. Okay. And then the next thing we did is we thermocoupled a tire on a dynamometer and measured the internal running temperatures at various positions close to the belt edge of a running tire. Okay. And this is kind of a big jump and hard to understand, but in our fourth session, we've focused totally on diffusion limited oxidation models. Kind of, if you come back for the fourth session, you'll understand. But here we're using the diffusion limited oxidation model to predict the oxygen consumption rates. And this, we do that twice, once for the stationary tire, and then secondly for the rotating tire. Okay, and so here we're going inner liner, ply coat, belt package, tread base, tread. And the way we're incorporating the effect of oxygen partial pressure in the cavity of the tire is two ways. We've the input to the diffusion limited oxidation model requires the term beta, okay? And beta is a term that is basically the effect of oxygen partial pressure on oxygen consumption rate. So we use our experimentally derived beta terms instead of our literature values, okay? And then secondly, when you use the diffusion limited oxidation model, you can input the oxygen partial pressure on both sides of your laminate. So here it's atmospheric partial pressure of oxygen. Here is, you know, the 30 psi, or the you know, the inflated tire oxygen partial pressure. Air pressure is 30 psi. The oxygen partial pressure is 21% of that. Okay, and then we run the DLO model to predict the oxygen consumption rate of the running tire. Okay, and again, we incorporate the experimentally derived beta term, and we have the oxygen partial pressure, and we also have the temperatures of these compounds that we obtained by thermocoupling a tire on a road wheel. Okay, so what we're after is this number right here, you know, 1.8 times 10 to the minus 11th, you know, and this number right here, you know, 1.2 times 10 to the minus 12, okay. So here's the 1.8 times 10 to the minus 11. Here's the 1.2 times 10 to the minus 12. Okay, so we're going to calculate the oxygen consumption rate of the field tire, which now includes the effect of oxygen partial pressure and duty cycle. And here's the oxygen consumption rate in the belt coat of the stationary tire, and here's the oxygen consumption rate of the belt coat in the running tire. So here's the oxygen consumption rate from DLO model times, you know, 4%. And here's the oxygen consumption rate of the stationary tire times 96%. Okay. So this is the oxygen consumption rate of the, you know, what should we say, the predicted oxygen consumption rate of the field tire. I make a note here that even though the tire is only 4% of its life is a rolling tire, this value is 40%. This 40% of the aging is coming from your driving time. Okay, so now, you know, in our earlier work, we had predicted the oxygen consumption rate at 22.6 degrees C, and now we have this oxygen consumption rate of the field tire. And the ratio of the rates, the relative rates, which is shift factor. Shift factors are relative rates. Okay. So now we have this shift factor that incorporates these two additional effects of 2.05. So what I want you to see is this red arrow right here. Okay, so you know, 2.05. You know, we were using this number right here for 22.6 degrees, and now we're saying that really it should be 2.05 times higher. Okay. The new shift factor accounts for oxygen partial pressure and duty cycle. This shift factor that we calculated. So here was our predicted curve, which we were so disappointed in. But you can see, you know, if you know, 10 years is about 260% elongation to break, and you know, if there's a factor of 2, that's going to bring it down to 5 years. So now this data is going to be, instead of being 10 years, it's going to be 5 years. So we go ahead and shift our data that way. And here's a comparison of our predicted elongation to break data. And here's our in-service tire data. So that that is the story of how that was obtained. So in summary, we say combining oxidation kinetics and tensile aging studies provided a way to predict property decay in an in-service tire. The empirical shift factors were a linear function of inverse temperature with an activation energy of 22 to 23 kilocalories per mole from oxygen consumption rate, CO2 generation rate, carbon monoxide generation rate, and elongation to break data. The predicted belt coat compound elongation to break as a function of time was obtained at Phoenix, Arizona, average ambient temperature 22.6 degrees. To correctly predict belt coat elongation to break changes, the effect of oxygen partial pressure, tire inflation pressure, and in-use running time were incorporated. This technique provided a predictive model for belt coat property elongation to break decay for the BF Goodrich tire. And we say the physical property decay observed in service can be attributed to oxidation. Okay, so there are 4 questions. I mean, maybe could kind of start the question and answer period. There's kind of 4 questions that I have. One was, how did we measure oxygen consumption rate? Second was, how we determine shift factors, and a better explanation of the term beta, and a better explanation of the diffusion limited oxidation model. So here is our oxygen consumption measurement techniques. Okay, so this is our vacuum manifold. Here's our pressure transducer. And then here's our reactor, stainless steel reactor. And then here's 3 more of them sitting here. And then here's our light gas GC, which allows us to measure the concentration of oxygen, nitrogen, CO, CO2, and also volatile hydrocarbons. So we cut the rubber into small pieces and stuff as much of the rubber into the stainless steel reactor as possible. And then we put it on the vacuum line, and we pull vacuum and then backfill with atmospheric partial pressure of oxygen, and we put it in the oven. And then weeks later, we put it back on the vacuum manifold and measure the change in oxygen partial pressure. And then we also push the gas into the light gas GC and measure the oxygen partial pressure from the light gas analysis. Okay, so second question that I asked was how to determine shift factors and generate a master curve. Okay, so here I have an example. Okay, so here's elongation to break as a function of aging time, 70, 80, 95. So might have data that looks like this. Okay. And so you want to generate these shift factors, and you want to obtain master curves. So here, the 70, 80, 95 degrees has all been shifted to 80 degrees. So here is the 80 degree data down here, and the shift factor is 1. So there was no shifting. Okay. So what we want to talk about is the 70 degree data. The 70 degree data was shifted horizontally to the right. We call it empirical shift factors. That means we're shifting the data until by eye we see good overlap. It can be done mathematically, but we say the eyeball technique actually is a bit better than mathematically minimizing the differences. And so here is the 70 degree data, 70 degree aging data, 1 day, 3 day, 5 day, 10 day, 15 day, 20 day, 30 day, 40 day, 50 day, 60 day. Okay, and here's the elongation to break. Okay, so the first thing we do is we take the log of the aging time. So here's the log of those values. Okay, so this, and then we're going to shift that data. So the shift factor is multiplying. It's the factor we multiply times to obtain good overlap. But adding logs is the same as multiplying times the shift factor. So we take the log of the shift factor, and then we add the log of the aging time to the log of the shift factor, and get the log of the shifted time, and then we take the anti-log. So you can see now 70-degree data elongation results, instead of being shifted, 60 days, it's now shifted 31 degrees, 31 days. Right? So, and then instead of 50 days, it's now 26 days. So the 70-degree data, used to be out here, and now it's on the eight shifted onto the, so it's, shifted time in days at 80 degrees C. Okay. All right. Third question I asked was, how would you explain beta? And beta is the effect of oxygen partial pressure on oxygen consumption rate. We say the dependence of oxygen consumption rate on oxygen partial pressure has been described mathematically by a term called beta. Phi is the oxygen consumption rate, and P is the oxygen partial pressure. Okay. The reference condition is atmospheric oxygen partial pressure. So we determine beta by curve fitting using a plot like this. Okay. So here is our experimental data, the blue diamonds, and then we fit, model fit, and until we get good agreement with our model fit by varying beta. Okay, this is the last slide. So I asked the question, can you explain the DLO model? So this is diffusion limited oxidation model. So diffusion limited oxidation model combines the effects of Fickian diffusion and oxygen consumption. Oxidation reactions use up the dissolved oxygen faster than it can be replenished by diffusion. Thermal oxidative degradation of compounds and rubber goods are often influenced by diffusion limited oxidation. So I said that the details are to come. I'm going to describe the diffusion limited oxidation model in the October 23rd webinar. And I might conclude by mentioning, the future webinars. Next week, we'll be talking about the aging mechanism, the chemical mechanism of aging. And then 2 weeks from tomorrow, we'll be talking about rubber aging, where we try to cover a broad range of polymer types and various aging issues, types of aging, and then in 3 weeks we'll be talking about modulus profiling and diffusion limited oxidation model. Thank you for joining the webinar. I enjoyed presenting it. I hope you enjoyed and learned something. This time I'm glad to try to entertain questions.
Yes, thank you for such a voice presentation, Dr. Terrill. It was really enlightening to hear the different and various of the models which are there in this particular vertical. Now we have few questions with us, and in order to put it across, the first question is from Ms. Devi Sara, where she is asking that how do we determine the shift factor example? That is, how do we achieve shift factor of 70 degrees Celsius to 0.52 and at 80 C to 1?
Yeah. So, very good question. So, let's look at this curve. You know, so here's the 70 degree data, and we want to shift that onto the 80 degree. So and we're just doing a horizontal shift. Okay. And so we're varying this number, and then, you know, these cells all have calculations. And it was the way we set it up. So we can quickly just vary this number right here, you know, 0.51, 0.50, 0.53, 0.54, and then watch how this, you know, automatically gets shifted, and until, you know, by eye, we say we have very good overlap between the 80 degrees data and the 70 degree data. So, you know, we're transforming these times into these times, you know. So you're just, you know, the way we do it is by adding logs together rather than multiplying. So we take
Dr.
the
Terrill,
log.
in the fourth column, what the AT signifies?
That's a shift. That's a shift factor.
Shift factor.
So yeah, right. So one way to do it is to multiply this, you know, time. If you take this times this, you know, you'll get these numbers. The way we usually do it is we actually take we're taking the log of these aging times, and we're taking the log of the shift factor, and then we add those two together, and then we take the anti-log and get maybe, you know, we don't have to do it that way, but so this, you can see, you know, this this number, this column right here is basically the shift factor multiplied times the aging time.
Right.
And then, and now we're plotting, you know, the elongation to break data versus this transformed time. So now we call this the you know, shifted aging time at 80 degrees C.
Right. I think that explains it. Yes, that how we are going to get that. The second question, Dr. Terrill, is that how do we measure the oxygen consumption rate? Is there any machine involved for that?
So this is a light gas GC and vacuum manifold, and then our reactors. So, you know, here's one of the reactors attached to the vacuum manifold. Here's three more reactors shown down here. So we cut the rubber into small pieces and stuff as much rubber as possible into the reactor. And then we pull vacuum and backfill with oxygen partial pressure, and then take this off the vacuum manifold, put it into the oven. And after weeks in the oven, we put it back onto the vacuum manifold, measure the change in oxygen partial pressure two ways. One by the pressure transducer, and then also by the GC, analysis of the gas, which we push from the reactor into the GC.
Okay. Okay. So the next question to this rate would be that how can we correlate with non-inflated rubber good like rubber gasket or mats or sheet?
So, I think, that you would find this in-service tire came from a tire, but if it was a sheet or a mat that doesn't have, inflation pressure, that you don't need to do the steps, step 3. You probably do need to think about duty cycle, and then sometimes you need to think about crack growth or UV exposure or ozone exposure. With a tire, UV and this Bilco compound is internal component, so it doesn't really see ozone. So oxygen seems to capture everything, but with a tire, you do need to understand the effect of the oxygen, the cavity pressure of the tire, which increases the oxygen partial pressure, and also you need to know that duty cycle. So I think like you say, you don't need to incorporate the effect of oxygen partial pressure higher than atmospheric, but you do need probably to think about other things. In that case, I kind of go back to my first slide and try to think about what's the major thing, or sometimes you have to think, like we kind of guessed oxidation, and went with oxidation, but then we found that there were 2 other factors that we had overlooked. So, if you capture the major one, and then maybe you have to incorporate a second or third factor.
Yeah. So in that entire process, Dr. Terrill, while previously you were on the slide of the elongation, and a very reasonable question has come from that perspective as well, that is there any special reason to choose elongation at break?
That's a very, very good question. So you want to try to identify the most critical part or property. Like for some it might be compression stress relaxation, or others it might be crack growth resistance. So elongation to break, it's easy, and if that works for you, it's really great. It seemed like elongation to break was quite sensitive metric for us, and it's kind of representing the ability of the tire to resist crack propagation. So I would say if it's kind of like, if you don't have anything else, you can choose elongation to brake because tensile property is so easy. So I think we chose it for ease, and then we also chose it seemed, to be working really well.
All right. Also, Dr. Terrill, while a few moments back when we were talking about the aging properties as well as the use of oxygen and the role of oxygen, so a pertinent question has come in that part as well, that in the absence of oxygen, no aging will happen. Then how did aging? Did that aging thing in an inert atmosphere?
Yeah, that's a very, very good question. We'll try to talk about that next week. So, if the rubber component is very thick component, for example, and diffusion limited oxidation, you can imagine that the inside part is actually under anaerobic conditions, and that can happen, in heavy tires. And so you actually, you'll see the modulus go down. We say that we suspect thermal reversion. And so it's, in order to duplicate that, well, actually, in 2 weeks from now, we're going to talk about that. So we use the same reactors, but we make sure that all the oxygen has been scrubbed, or all the oxygen has been removed from the reactor, and then we can put it into the oven and age it at different times, different temperatures, under pure anaerobic conditions. Mm-hmm. And that's a very real life situation also.
Right. So it was largely in the inert atmosphere which we have been carrying about.
Yes. Yeah.
Right. Great. So this was it for the question. We had some more questions from a few more participants, but I think in the interest of the time,
yes,
we'll keep you posted with the questions. And I again humbly request all my participants and all the members who have joined the session today, if you have any queries or questions to Dr. Terrill regarding this subject, please post those questions to us, and we'll certainly get it responded by Dr. Terrill. I also would like to repeat, yeah. You were saying something, Dr. Terrill.
Yes, I welcome that. Mansoor said he was going to send out my email or your email, and if questions come up later, we try to answer them.
Absolutely, that's so kind of you. We will certainly share the question from the